Hi everyone, how's it going? Today we're going to start going over the AP Physics 1 Mechanics curriculum, so we're going to start with kinematics. Now kinematics we can look at in two different phases basically. We could look at it in unconstant acceleration, where you don't have a constant force acting upon it and where you don't have a constant acceleration, or you have constant acceleration. Now for those of you in AP Physics 1 or have taken AP Physics 1 in the past into Physics C, you might be more accustomed to these three equations, right? Because all three of these equations are derived from assuming a constant acceleration. We have a video on that. We'll link it down in the description below. But how this actually goes is that as you move forward in AP Physics C, you have these systems where instead of using these work arguments that you might be able to use on constant acceleration, such as spring systems before, now you're trying to look at displacement over time, or displacement as a function of time in a spring system, or things like that, or what is the velocity of a free-falling object that is experienced aerodynamic drag over time, right? And then from there you can find displacement and acceleration, which are the integral and the derivative of that function respectively. But first let's start going over the process of constant accelerations, then we'll move into a problem with a free-falling object that is experiencing aerodynamic drag. So starting with constant acceleration, right? So these problems we should be more familiar with, such as a ball being dropped off a cliff, where you have a constant acceleration in the y direction due to gravity. If you have a ball thrown off a cliff, you might have some direction in the x direction. So if you give an initial velocity, but it accounts for both x and y, that might be something you have to break up into x and then y, right? That's something we might have to be mindful of. Furthermore, if you have a more complicated system, such as if you have a ball rolling off a ramp and then rolling on a table and then falling off the table itself, you might have to split up that system in three different ways, right? So phase 1 is the ball rolling off the ramp, phase 2 is the ball rolling on the table, and then phase 3 is the ball falling onto the floor. This can be very useful because if you look at the sum by itself, you have many changing velocities here and you can't really make sense of what you're trying to write. So doing this will really help you in the long run. Last important note when you're doing constant acceleration problems is that sometimes you might have to bring in work or energy arguments into here, such as the conservation of energy. You might have to look into work such as the integral over time, but that's over displacement. Sorry, that's things we'll go into a little bit later. And finally, the main thing that we're going to look at is that after you've done all your calculations, after you've done all the things that you've actually done, it might seem silly, but reread that question, right? Because if I've done some problems where you've done all the calculations, maybe find time, but then you're actually looking for the displacement in x, and you forget to plug it back in, and that can cost you several points that are very easily avoidable. And you've done all the calculations right, but you just got to make sure you read that question. Now moving forward, now let's get into unconstant acceleration. Now unconstant acceleration is slightly harder because from here you have to look at more instantaneous changes. So this is where it starts involving more of that calculus part. So let's start off with an example for unconstant acceleration. We can have many examples such as a spring system or a pendulum, things like that, but we're going to start off with an example like this. So we have a block falling, free falling. So there's the force of gravity, but we're also going to include aerodynamic drag. So the main idea behind dynamic drag, especially in physics C, is that they make it simpler for you, right? So they don't include all these extra factors that might come into effect when you have all these molecules bouncing off each other. So what they often do is that you have this force right here that increases over time because you make it proportional to velocity, right? So this proportionality, let's say if it's linearly proportional, we can then write it as the force equaling some constant proportionality times v, right? And logically speaking, as the object moves faster and faster, which will happen because of this force of gravity pulling it down, it will hit more and more air molecules, which will then increase the friction on that object, right? So the faster you go, the more particles and molecules that you run into, resulting in more drag. So this makes sense for a preliminary basis. Now from here, what we're going to do is that we're going to go, that we're going to count the force of gravity as being positive and the drag on it being negative, just to make it life a little bit easier. And from here, we're just going to set up our basic force equations, right? So we're going to have the summations of forces. We could add y, but there's no forces in x, so it doesn't really matter. Is equal to, well, NA, which all this is equal to FG minus F. Now writing the preliminary equation might be trivial, but many times you can get points off just writing it in vector form. From here, what are we going to do? Well, if you look at it closely, we have m and we have acceleration. Now, acceleration is equal to the change in velocity over the change in time. Right? So we have acceleration is equal to delta x, or delta v, sorry, over delta t. Now, if you want to look at it in more practical terms, so we're going to start including calculus into this. We're going to look as acceleration not as a discrete measurable thing, but as an infinitesimal change in velocity over an infinitesimally small change in time. So by doing this, we have acceleration is equal to dv dt. So what we get is m dv dt is equal to, we have the force of gravity, which is mg minus, and then we can have bv. Now this is what we can call a differential equation, right? We have our dv dt and we have v. So this is our first order differential equation right here. So how are we going to solve this? So we're going to start doing some math, right? So we're going to divide this whole side over to get v on the same side as dv and multiply dt on the other side. What we end up with is going to be the integral. We'll assume that at t equals 0, we'll have v not equals v, just for initial conditions. We'll have from 0 to v of t, which is what we're trying to find. We're trying to find the velocity function of the block in terms of time. V of t, and we have dv over mg minus bv is equal to integral from 0 to t of 1 over m dt. From here, what we're going to do, well, we can take the integral, right, of both sides. We'll have the integral of, this basically is 1 over v, right? So the integral of 1 over v will be ln. So we have the constant on the side, so we're going to do negative 1 over b, ln of mg minus b v of t. And then, of course, when v equals 0, so we're going to subtract it. We're going to have ln of mg, so minus ln mg, so we'll have an mg on the bottom due to logarithmic rules. And then we'll have equals t over m. Now from here, what we can do, we're going to multiply negative 1 over b to the other side. And to get rid of this ln, we're going to lift both sides up to the e, using the e function. So from here, we're going to do mg minus b v of t over mg, we'll multiply the mg over as well, equals, we'll have mg e to negative bt over m. And from here, we'll simply have v of t is equal to mg, factoring out that mg over b, because you have to divide the b over to the other side, 1 minus e to negative bt over m. And that is our velocity in terms of time. Now, if you want to find displacement, or if you want to find acceleration, we would integrate or differentiate. So as a quick example, if you want to find the acceleration, we can just integrate, we just differentiate. So because velocity, so if you differentiate the velocity in terms of time, so d dt on both sides, you end up with dv dt, which is equal to acceleration. So if you want acceleration, a of t is equal to, this is just a constant, so that just goes away, and we end up with mg over b times negative e to the negative bt over m. Okay, so you take that derivative, you have b over m, so those will cancel out, and you'll be left with g e to the negative bt over m. Displacement requires a little bit more work, so what we're going to do is we're going to go from here, we're going to look at velocity as a change in displacement over a change in time, right? So if we're going to look at it the same idea from here, we have velocity is equal to delta x over delta t. Now, for same purposes, we'll look at velocity as an infinitesimally small change in displacement over a very small change in time. So from here, we'd have a differential equation in terms of time, right? So we'll have dx dt is equal to mg over b 1 minus e to t over m. From here, we multiply the dt over to the other side, and we integrate both sides, right? So if we integrate both sides, we'll have 0 to x of t of just dx, basically. We could take these constants over to the other side, right? Because it makes it easier for us. We'll have b over mg, and then we'll integrate. From here, we'll integrate from 0 to t of 1 minus e to the negative bt over m dt. Right. So what we're going to do from here is just integrate this. So we get 0 to x over t. So we have b over mg of x of t is equal to, this is a little bit more trickier, but we have a constant right here. So the integral of the constant is just t. T minus, now this is where it gets a little bit more tricky. We have a negative, so this becomes plus. We have m over b, because if we differentiate b over m, we'll multiply it down or get 1 from that constant. We'll have m over b, e to negative bt over m. And then from here, we also have a 0 right here. So we've just integrated from t, and so we'll have minus, and then at 0, we'll have 0t. And then multiplying 0 here, we'll have e to the 0, which is just 1, minus m over b. And so this will give us our final displacement equation of, just putting in writing, mg over b t plus m squared g over b squared e to the negative bt over m minus m squared g over b. Another question, our final question we'll answer today, is the idea of terminal velocity. Now, what they like to ask sometimes about terminal velocity is, what is it, right? So terminal velocity is at one point, do the aerodynamic drag force cancel out the force of gravity. At one point, you're not accelerating anymore. So with that argument, terminal velocity is when you reach the maximum velocity you can off that free fall, right? So because of this, both forces will cancel out, as I said before. So from here, we'll have the summation of forces is equal to same force argument here, but instead of equaling it to ma, we'll equal it to 0, because this is the point where we're no longer accelerating. We've reached our final velocity is equal to 0. Which, from here, what we can do is we'll have bv is equal to mg, and so we'll have our velocity equal to mg over b. So that's basically it for aerodynamic drag on a free-falling body. Mostly just keep in mind when we're doing kinematics, things like this, when you can assume a acceleration to be constant, or when you can't assume this, it's going to be an unconstant acceleration. And doing this will prevent silly mistakes in the future, right? If you're going through the process, make sure that you have your list of givens, you've written it down. If you have to split into 2 dimensions, such as x and y, go ahead and do that, right? If you don't have an acceleration in the x, when you do that, you have x, v, and t, right? Compared to y, which will have 2 velocities, velocity initial, velocity final. You have an acceleration, a time, and a displacement, so you have 5. And the main link between the 2 of them will be that time constant, right? So if you have to find out things like that, you could just split it up into 2 and find that length through that time. Finally, in non-constant acceleration, make sure that we don't resort to these equations, because these equations will not work, such as if you're trying to find maximum displacement off of a spring, do not use these because the acceleration on that spring is not going to be constant, right? Because that's another differential equation, actually. That's something we'll get into a little bit more into a different video. Because, for example, you'd have m, and then from here, doing this, we have acceleration is, if you plug this back into here, we have the second derivative in terms of time of displacement. And so, with Hooke's law, which is for later, would have kx, right? So that'll be another differential equation that we'll solve and look for the period of the spring and things of that sort later on. I hope this helped, and have a good day.